Okay, in this video we're going to go back to some more examples of matching position time graphs to velocity time graphs. So the first one I have here, oftentimes we see it as like just a whole long progression of motion, a big long x versus t graph. The key point to remember is slope of this graph gives us this graph. Okay, same principle applies. So first thing I want you to do is break this long curve into different segments where the way that the slope is changing kind of differentiates. So the first segment I'm going to put is here, where its position's not changing, and then from here to about here I have an increasing slope, and then from here to here my slope is decreasing where I'm at a maximum position, and then from here to here it's a decreasing curve, and then from here to here it's a straight line. From here to here it flattens, there to there, decreasing, and then back to increasing. So everywhere the way the slope changes, there's a discontinuity there, put a dot. That'll help us break the segments into two smaller chunks. And then let's just take it segment by segment. So here, position doesn't change, flat, slope is 0, velocity is 0. Very easy. From here to here, my slope is increasing positive, so my velocity is increasing positive. From here to here, I'm going from steep positive back to flat, where velocity is 0, so I'm going back to a velocity of 0. Now here I'm decreasing in the negative direction for a while. Now the rate of change from here to here seems to be the same, so I'll keep the same slope. And then at this point I straighten out, so my slope remains constant, negative and constant. So my velocity is negative and constant. Okay, so from here to here I'm increasing again, going from steep negative to close to 0, maybe not quite 0, almost reach a velocity of 0. And then go back to becoming more negative. And this is a little steeper than this, so I'm going to come down a little bit lower than I was here. I'm a slightly lower velocity. And then again I go to increasing back to 0. Okay, so I was able to construct this entire VT graph simply off of breaking it into segments, my XT graph, and then asking how the slope changes. Is it positive? Is it negative? Is it increasing? Is it decreasing? And that really is the way you match it up. Now, sometimes you're going to run, that was a smooth curve, sometimes you're going to run into what appears to be discontinuities in the position time graph, or where there's an abrupt change in slope. So in this example, you'll see there are some instances where there are discontinuities in the slope, or what you might call sharp corners, where there's an abrupt change in position. So I'm going to show you how we handle these. Really, the rules don't change in terms of using the slope of this graph to tell us this graph, breaking it into segments. So let's do that first. So segment 1, segment 2, 3, 4, 5, 6, 7, 8. Everywhere the slope changes, or the way the slope is changing changes. It's a little wordy, but hopefully you get the idea. Alright, so I start at a negative position and I move in the positive direction, so with a positive slope, so I have a positive velocity, and it's a straight line, so it's constant. So I start with a constant positive velocity. Now here I abruptly change. I go immediately from a lower velocity to a steeper constant slope, which is a higher velocity. So whenever we have a sharp corner, we have a discontinuity in the velocity time graph. I jump right away to a steeper positive velocity or a higher positive velocity. Now from the transition in this segment to this segment, I start to slowly flatten out to a velocity of 0. So here I would begin to decrease my slope and decrease my velocity towards 0. And again, now there's a continuity here where I slowly increase back to a high constant positive. Slope goes from flat of 0 to increasing steeper in the positive direction. Now here I have a discontinuity too, where I go from a fast positive velocity to no motion at all, to stopped. So notice I'm showing these discontinuities with a dotted line. Okay, velocity of 0. Now I start at 0 and I slowly get decreasing in the negative direction. So I'm gaining a negative velocity. Now here there's another discontinuity or sharp corner. So I go abruptly from steep negative velocity to flat of 0. So go up to velocity of 0 and then I slowly decay again into another steep negative velocity, but maybe a little bit steeper. This is steeper than this, so I'm going to a greater negative velocity. And then I have another discontinuity or sharp corner where I go from a negative velocity to a positive velocity right away. And then that flattens out towards 0, almost 0, not quite. So I'm decreasing like such. So it's important to note that in real life, I mean, we really don't have sharp corners necessarily because there's a continuous motion from one stage to the next. But in interpreting the graphs from position time to velocity time, it's important to note that what that would look like in terms of matching up segments where there isn't kind of a smooth transition from one section to the next. Okay, the last thing I've got for you in this video is a practice. So I want you to jot down this position time graph. Notice there's some smooth transitions and some rough transitions. I want you to first mark out all the segments where the way the slope changes is different. And from that point, map the velocity time graph. So you can mark this down, pause the video. Okay, and here is the solution.